So this is the day we're going to talk about elliptic curves, and then there's only one more class after this, and then the final. The last class I'll talk about TLS, which is an important topic, but I made the quiz extra credit because it's so late in the semester, really. Anyway, but the elliptic curves I'm very pleased to talk about. It's a wonderful topic, and I've been learning a lot more about it. So anyway, that's what we'll talk about now is the elliptic curves. And I should have those slides. All right. I keep updating the slides and then having the viewer closed. All right. So, here we go. All right. Looks like we're in the business now. All right, so we're going to talk about what an elliptic curve is and the elliptic curve discrete logarithm problem, which is the difficult problem that makes it possible to use it for cryptography. And then you can do a Diffie-Hellman key agreement over it, and you can sign with it. There's an issue of choosing what elliptic curve to use. Now remember, in RSA, you multiply two prime numbers to make this exponent n, but it turns out that there are some prime numbers you should not be using. If you do, it will turn out to be insecure. And the same thing's true of elliptic curves. There are a lot of elliptic curves, but you have to choose the parameters carefully because some of them are not secure. And then we'll talk about some attacks on elliptic curve cryptography. So ECC is basically the new improvement over RSA. The primary advantage of it is that the numbers are much smaller, so the math is much faster. So it's much less calculation to use. Your 256-bit elliptic curve key is stronger than a 4096-bit RSA key, and since it's much smaller, it's of course much faster to do the mathematics. All right. So it was developed in '85, but nobody bothered adopting it because the same thing I've said forever in this class. Once there is something already out there that is pretty good, as they invent better stuff, nobody cares. They'll just keep using the standard thing that works, and the standard thing was RSA, so nobody really cared about using ECC for a long time. But they finally started doing it starting about 16 years ago. And Bitcoin used elliptic curve, which was more about that later. All right. And so now a lot of modern applications do let you use elliptic curves because it saves processing time, battery power, and ultimately money in that regard. So an elliptic curve is this thing, y squared equals x cubed plus ax plus b, so it looks something like this. And so you've got, one thing is the only thing determined is y squared, so every point xy that's on the curve, the point x minus y is also on the curve, which is why it's symmetric across the axis, because you only defined y squared, and so this negative number has the same square as this positive number. So, you can define it over integers, and then they just look like random dots in x and y, but only some dots are on the curve, and there's a way to add two dots and get a third dot on the curve. There's some way to hop around among these dots, which is all that really matters. And this is called a field. Now, a set is just a group of numbers or objects, and a group is a special group of those that had certain properties like the identity element and stuff, and a field is the next thing, a special kind of group, and this is where you have two operations, which you can call addition and multiplication, and both of these are closed in the group. So you can add, there's an identity element where if you add 0, you still have the original value x, there's an inverse for addition, and there's another inverse for multiplication, and adding any two items on the group lead to another item on the group, and multiplying an item on a group by a value returns you another item in the field, and that's what you call a field. This with two operations possible, addition and multiplication, although they could be any operation that take one element of the field and move to another element on the field, but we can call them addition and multiplication just for convenience. All right, so you define addition. What's that? Confused about this because Q does not have a Q does have a multiplicative inverse. Everything has a multiplicative inverse. That would be 1 over Q. So we'll talk. Let's go ahead. Oh, 0. 0 does not have a multiplicative inverse. Well, I'm not sure that's true. In elliptic curves, I think 0 probably does have a multiplicative inverse, but it's a very good question, and I really don't know. It may be that you don't need the 0 element to have the multiplicative inverse. Or it may be even more evil. Well, it's a good question, and I don't know the answer. Let's see if it appears coming up here. Other than that, I'm not quite sure. You've got a point. But remember, this is not really normal multiplication or normal addition. So it might be that a multiplicative inverse of 0 does exist. That's an interesting question. Anyway, here's how you add 2 points, which is just an arbitrary way to move from one point to other points. It doesn't have anything much to do with normal addition. You have a point P and a point Q, and the rule is find the other point on that line, connecting them, and then reflect it through the y value. So this is just a way to combine 2 points to somehow find another point that's on the curve. I don't even know why you'd bother calling this addition. It doesn't seem to have anything to do with normal addition. But anyway, it is a way to combine 2 points to get a third point that's on the curve, and that's all you really need. So P plus minus P is going to be this. Here's P, and now, by the way, notice minus P, you make the y value negative, but you don't make the x value negative. So again, it has very little to do with what we normally think about as negative numbers. But here, that gives you 2 points like this. So the third point that it points to is the point at infinity, way out here. So P plus minus P is the point at infinity, which you write as 0. And by the way, you know, it might be fair to say that 1 over 0 is 0. And, yeah, I don't know. We'll see. Actually, I think that's probably it. I think the multiplicative inverse of 0 is probably 0. But anyway, I'm not sure. Anyway, that's the point at infinity. And then the other thing you might want to do is add a point to itself. And the rule there is use the tangent line. That will take you to another point and then take the inverse of that one. Why is P plus minus P infinity? Because, remember up here, when you combine these two, P and Q, you connect them with a line and you find the other point. But if you combine P with minus P, this is the line, and it never crosses either of the curves again. So the point where you say it crosses the curves is out here. The point at infinity is infinitely far away all the way around. There's no other point, but you call all that circle out there infinity. That's why it doesn't really map very nicely to normal things like addition or multiplication of integers or floating point numbers at all. That's why I mentioned these. I'm not sure it's really helpful to use these symbols like plus and minus. We're just talking about a way to take 2 points and find another point. And it's not really bearing a lot of resemblance to the stuff we normally call addition and multiplication and subtraction and such. And it doesn't really have to. All we need is for it to satisfy these properties where there's some way to combine numbers and there's an inverse and so on. That's why, you know, my friend who understood this much better than me when I was a teenager used this to solve Rubik's Cube. And he said, you know, all the possible places you can put the little colored boxes on the cube, that's a group of numbers, and there's a way to transform it from one to the other. And he understood what this really meant. It's just you have some group of things and you have some rules that move one thing to another thing. Doesn't really have to have anything to do with addition or multiplication or anything. It could just as well be dice you're rolling, and there's some way to move from one set to the other, and then some way to reverse it. He understood that, and I didn't really. I thought in terms of normal math, and I couldn't understand how you could solve Rubik's Cube with group theory. But he did. And that's why all computers are essentially finite state machines. There's just a bunch of bits, and the bits are in a state, and then there's a program that will move it to another bit, another set of bits, and there's some algorithm is just how you move from one set of bits to the next set of bits. You know, it doesn't really connect to math. It's just a finite state machine, and that's what we're talking about here. You have some set of points on the curve, and have some way to move from one point to another. Anyway, so that's what this one does. That's how you can define adding P plus P. And so now we can talk about multiplication. So you just add P many times. So if you want to multiply by a constant K, you could do it with K addition operations. But the addition is pretty clumsy, and of course you can make it much faster, so it's really log K operations by instead using P plus P to get P2, then add P2 to P2 to get P4, and this to get P8. First double all of them, and then just combine these to get the ones you want. So you have to do essentially log P additions, log K additions, instead of k additions. Anyway, it's just a matter of making it faster. It doesn't change the result. And so now we define a group. You have a bunch of elements, and individual elements we're going to talk about are x, y, and z. Some kind of operation with these properties. If you take two elements in the group and you multiply them, the result is in the group. And you can do the multiplication in either order and you get the same answer. There is an identity, so multiplying by that gives you x. And there's an inverse. For every x, there is an inverse, which will take you back to identity. So that's the closure property of the group. All right. And so addition is also another operation. So if P and Q are in the group, P plus Q is, you can do the addition of three objects in any order. There's an identity element, so that if you add that, you just get back to P. And there's an inverse, so you can get to 0. So those are the necessary properties required. Now, the inverse, that's why I'm looking at this, and I really think the point at infinity is its own inverse. Because I look at, it's its own additive inverse for sure. Now, multiplicative inverse for the point at infinity, I need to have something I could multiply by infinity to get back to 1. But I don't really know what, I think the identity element is also the point at infinity. So I think the point at infinity is its own inverse. I think that's what happens. There's a question. I think 1 over 0 is 0 in elliptic curves. That's what it looks like to me. But it would be good to Google and find an authoritative statement from somebody. But that's my feeling. I think 1 over 0 is 0 in this crazy world here. All right. So now we have a field. We can define the discrete logarithm problem, which works like this. You're going to have P and Q, and I want to be able to find K, so when you multiply K times P, you get Q. That is the discrete logarithm problem, and that's turned out to be, people believe that's as hard as the other discrete logarithm problems on which all of our public key cryptography is based. And it seems to have held up for about 40 years, so it's not like the math is beautiful and perfect like you might want it to be, but it seems to be as good as any other public key cryptography, all of which, by the way, is not all that strong and likely going to get trashed by quantum computing in a couple of decades. But for right now, it appears to be the case that if you choose the curve correctly, nobody can find your private key from your public key. Your public key is this product of KP, and your private key is K, and nobody can find it. All right, so this is much faster because the numbers are much smaller than RSA. It's much faster than RSA. The security is n over 2 bits, they say. So if you have a 256-bit key, you'd get 128 bits of security. And as we said, that is enough. 100 bits is probably enough. Nobody will ever have enough time to do 2 to the 100 calculations of anything. So if you have 100 or 128 bits of security, that should be unbreakable unless there's some kind of shortcut in the math. And so that's why you can see that's a whole lot shorter, 20 times shorter than RSA. That's why people say this thing runs much faster than RSA. All right, so you can make Diffie-Hellman key agreement the same way. So here's how it works. You make a secret key A, and here's Diffie-Hellman. You pick a number A and you transmit G to the A. Then the other person chooses B and transmits G to the B. And now you take the other person's public key to your secret key, and you end up with G to the AB. This is Diffie-Hellman. You create this number from the other person's public key and your private key, and even a person that holds both of those public keys cannot figure this number out. And here's how it looks with elliptic curve. Pick a random secret and multiply it by the generator and transmit that point. That's your public key. The other person sends a public key. And now you just multiply their public key by your private key. And again, you have a number here. DAPB is DADBG, and this is the associativity problem. I can multiply DB times G and then multiply by DA, or I can multiply DA times G and then multiply by DB, and we'll get the same answer. So now we have agreed on a shared secret and the stuff we have sent over the wire is the public keys, and because the discrete logarithm problem is hard, nobody can figure out the private keys from the public keys. So the logic is just the same as RSA. These all are very much the same. So that's now we have created a shared secret, and then we just have to turn that into a key and we can encrypt stuff. Now there's a signature algorithm, which is the one used in Bitcoin, and it's got a signature generation and a verification algorithm. It's used all over the place. So you have a private key, and the verifiers hold the public key, and they know what curve to use and the number of points that are on the curve, and a base point, G. These are the agreements. And so you hash the message. Then you pick a random number K. You have to add another random number. This is necessary, otherwise you would end up leaking your private key by signing multiple messages. So then you calculate a public key sort of to match that random number, and now your signature is these numbers here. One of them comes from your random number, and the other includes the hash value. So it looks a little screwed up, but the point is, this is a number that can be easily verified by anybody using only public values, and includes the hash of the message, and includes your private key to calculate it, and it includes your private nonce, K. So this turns out to be a way to make a signature, and I showed you that last time in the demonstration. That turns out to be very good, and it turns out, of course, also to be much smaller. These two values, R and S, are both 256 bits long, so if you're using 256-bit numbers, then you have 512 bits for a public key, or for a signature rather, which is pretty nice. It does, by the way, mean that, now remember, RSA was used for encryption and signatures. ECC can do a lot of things, but one thing ECC does not do is not encryption directly, because remember, if you're encrypting something, we hashed a message first. You can only send a pretty small message with ECC. Remember, the message you can send with RSA, the way it's written, is equal to the size of the key. So you can send a message up to like 2048 or 4096 bits, but the keys here are pretty short. So anyway, I'll get there in a minute. Anyway, ECC is much faster. The signatures are much shorter. Everything is much faster. So here you are signing something with RSA. Takes 7 milliseconds, but with ECC, it was essentially 0 here. They didn't give me enough spaces. Signatures per second. This will do 100 per second. This will do 21,000 per second. Much faster. To verify it is about the same. So it's very nice. Saves a lot of money, saves a lot of time. All right. And you could encrypt directly with elliptic curves, but if you did, you could only send about 100 bits of message that way, not even enough for a secure private key. That's why with RSA, what about the last column? Oh, the last column is how many you can verify per second. So it's just the inverse of these numbers. So you can verify 8,000 per second or 9,000 per second, about the same. But remember, in RSA, we carefully chose a small e and a big D, so encrypting would be fast, and decrypting would be slow and done on the server. And in ECC, both ends are as fast as the fast end of RSA. So it really helps. All right. Anyway, and the point is you could encrypt directly with RSA, but only a message less than about 4,000 bits. And if you did that with ECC, you could only send a message about 100 bits. So you don't use ECC directly for encryption. What you do, of course, is you take the shared secret and then run it through a key derivation and turn it into a private key, and then you use AES or something, which is what we did in the project I showed you last time. All you really need to is agree on a shared secret. You don't really need to use this algorithm for encryption. Once you have a shared secret, you can just use any kind of normal symmetric encryption. So here's what you do. You pick a random number D, compute a shared secret, then use a key derivation scheme to evaluate a key from that, and then use an authenticated cipher, like AES, a symmetric cipher. All right. So now the problem is, how do you choose an elliptic curve to use? This turns out to be pretty nasty. The formula is incredibly simple. Y squared is x cubed plus ax plus b. So there's only two numbers. You just need to choose an a and a b. Then you also need, all right, so now you also choose an order, which is the number of points to include. So there's really 3 numbers. Now, some curves let you calculate p plus p with the same algorithm as p plus q, and that would be nice, so you don't have a timing leak showing if you have p plus p or p plus q, that sort of thing. And as we're going to see, there are some curves that are weak, so it really would be good if the people that made the curve you're using would explain exactly how they derived these numbers. Otherwise, you might be worried that they've chosen numbers that make it possible to reverse it. Now, the NIST defined 15 curves that are recommended, 5 prime curves and 10 other using things called binary polynomials. So these are, in year 2000, the National Institute of Standards announced 15 official curves and said everybody should use those. All right, so here's the most common NIST curve, P256. The modulus is P, which is this number, which is just clearly simple binary number, 2 to the 56 minus 2 to the 24 plus 2 to the 192 plus 2 to the 96 minus 1. A long 256-bit number, but a very simple one with a whole bunch of zeros, very simple number. And then you use A is 3 and B is another complicated number. The problem is, where did you get this number B? And this is where people get worried. B is the SHA-1 hash of this weird number. And why? And the spaces I put in just to break it into bytes so you can see it, or somebody did. It's all just one long hexadecimal number. And they never explained it. They never explained where they got that number, and that is suspicious. Because the National Institute of Standards has been caught several times recommending numbers that have a secret backdoor in them so they can get in. It's always the same. That's the point. We use a curve, these numbers, it is suspicious. These numbers are always the same. You use exactly this number, this prime number, and you use exactly the SHA-1 of this as the B. It never changes. So they tell you to use these numbers, and they don't say how they got them. And they've done this several times, and they've been busted several times for having chosen numbers where there is something about that number that means if you know another secret number that was used to generate this, you can break in. And there is wide suspicion that that is true of this number. So it had the effect that when the U.S. government recommends that you use something, a lot of people decide not to use it. Yeah, your textbook author does not believe that there's a way in. But a lot of people do. Let's see. So this one here, let's go on to the next slide. This I just put in today. This is from a website. So they say, Bruce Schneier said, I no longer trust the constants. This is primarily because of Edward Snowden. Edward Snowden, had to flee to Russia after leaking a bunch of NSA internal documents, revealed how much the NSA is deliberately poisoning cryptography and pressuring NIST to lie about cryptography and telling people to use unsafe routines. They've been totally busted. They absolutely have done that. It's not exactly proven they did it from here, but Bruce Schneier, probably one of the most important cryptographers in the world, very influential, said he doesn't trust him anymore. He looked at random seed values. There's no justification given for this value, and he considers that smoking evidence that the parameters are cooked. And so, many people refuse to use the official government-recommended algorithms, and they use other things, like Bitcoin, Tor, and many other applications, use other ones that did not come from NIST. So, I'm not sure where the don't versus do is. It might be on some different slide than this one, which I just added today. What's the argument experts have for trusting that coefficient? I don't think there's any. That's a good question, and I do not know. This is almost a religious issue. Do you feel like the government is evil and plotting against you, or do you feel like the government is basically good and you can trust them? It's a whole lot like our current division in Republicans and Democrats in America. It's, of course, if you're writing something to be used by the military or the government, then you would use the official NIST curve, because that's what they want you to use, and they probably wouldn't approve anything that wasn't using the official curve. So if you are loyal to the government, you would say the NSA chose that curve to make us all safe, and it's better than these other curves. And if you mistrust your government, you would avoid it. And so you have two camps. And nobody really knows. However, what they've done before has been, they will have this number somehow generated from some private numbers. And if you know those private numbers, you can get in. But if you don't, then you can't get in, and this accomplishes the goal of the NSA, which is no bust. The NSA wants to have a secret backdoor, but nobody but us can use it. And they have done this many times. Well, you could argue that. I don't know. The people who trust the government and obey the government would say that if there is a backdoor in there, it's there for a good reason, and I want the government to be able to catch the terrorists and stuff, so I'll cheerfully use the official government encryption, which has the effect, which, by the way, I would agree with. I would be happy to have a system where the government can get in, but the crooks can't get in. That seems about right. Anyway, but nothing is proven. And nothing will be proven unless you have another martyr like Snowden willing to leak the secrets out from the NSA and then have to flee American justice forever as the result. So anyway, here's some other curves that are out there. Daniel Bernstein published this one, 25519, which is got P is 2 to the 255 minus 19. That's where he got the number. And it just has this number here, 48662, and he explains where he got it. And so you have no suspicious curves anywhere, and a bunch of people use this. But it is not the NIST standard. It's not the one the government recommended. Here's another one, SEC P256K1, where you've got 2 to the 256 minus these numbers here. This is the one Bitcoin uses. And again, A is 0 and B is 7. The curve is incredibly simple, x cubed plus 7. And again, that's not from NIST. It doesn't have any suspicious numbers in it, and it is considered secure. France has their own. Germany has their own. Germany also has these suspicious numbers in it, kind of suggesting that whatever the German equivalent is of the NSA has probably secretly backdoored that one too. Here's other ones out there. 41417 is another one. There's a Goldilocks one. You know, there are other ones out there that aren't used that often, but they are available. All right. So here's some flaws that can happen in ECC. Elliptic curves have more parameters and therefore more opportunities for mistakes. So you might make errors like having side channel attacks or timing calculation attacks, depending on how you implement it. So that's certainly true. The math is a little confusing, and you might make mistakes in writing your code. You might use bad randomness. Every time you sign something, you have to make a random key. So if you were to reuse the same nonce, then that would be a problem. And this apparently happened on the PlayStation. They didn't use a sufficiently random key. So if you reuse a nonce, you're in trouble. That's what nonce is, n once, a number you have to use only once and then not use again. So, of course, if you break that, then that weakens it. And then this one, which I was wonderful, I finally got this straight right before class, going over it again, the invalid curve attack. This is actually pretty brilliant. So remember, the idea is, let me go back to this the way it should be. To agree on a shared key, this person is supposed to make a private key and calculate the public key and send it over. This one, there, make a private key, calculate the public key and send it over. This person is supposed to make a private key, calculate the public key, and send it over. The invalid curve attack is where one person sends a malicious public key, which is not on the right curve, which is pretty brilliant. So, suppose I send a malicious number here, PA, that is in fact not on the agreed on curve. This person does not check to make sure that that number is on the curve, the way you would have if you did last homework. Let's say I demonstrated last week, where first thing you do is find the points on the curve, and they calculate, they multiply it by their secret key and send it back. If they choose a malicious curve, then they're able to reverse the discrete logarithm problem, essentially, because they chose the wrong parameters, and they're able to deduce your secret key. So if you just take whatever you get, multiply by your secret key, and send it back, that's not really safe. What you ought to do is take the key, verify that it's on the right curve, then multiply by your secret key and send it back. But if you don't do that verification step, this person can maliciously choose a key that's on a broken curve that's dangerous to use and therefore determine information about your key, and that works. It is pretty brilliant. And that really happened to some TLS implementations and some JSON libraries, and a big deal in 2015. You could, verification, well, you know, I think people didn't think verification was part of the process. They didn't think of that. They had to add it, you know. I don't know if it's in part of the official standard. there's an algorithm put up in the request for comments that define these things on the web. It's a good question. I don't know if it was a defect in the algorithm that was published or it was just a defect in the implementation, but they didn't check to verify it. Anyway, that's why people are afraid of cryptography. If you make one very minor little, skip one minor step, and the one we talked about a couple times ago was the padding oracle. If you just use an error message that has a little too much information, then you ruin everything. If you just use that nonce twice instead of once, you ruin everything. You got to really be careful and do everything exactly by the rules in your crypto. Even a small thing could shatter it like glass. All right, so let's see if I can get my cahoots up. All right, this will be 12 elliptic curves, okay? All right, I should have them here. Get past this advertising. There we are. Good. All right. All right. Let's see how it goes. All right. So how long should your key be? .256 bits is long enough. Otherwise there'd be no real virtue to this system. The short key is the main virtue. All right, how long of a message can you encrypt with AES? Any length, you've got blocks, and you can have as many blocks as you want, and there's various modes like cipher block, chaining, or counter mode. Any length of message you can encrypt with AES. Which curve is suspected of having a backdoor? This is the NIST curve, P256. That's one of the 15 NIST curves. It's the most common one, and it's the one with that suspicious constant in it. All right, how long of a message can you encrypt with elliptic curve cryptography? If you're just using elliptic curve directly. That's where, oh, all right, I thought it was the one with 100 bits. Let me see. I got, what's ECIES? Is that the one where you derive the key? It probably is. I may have given you a bum steer there. Oh, this is the one, the integrated scheme. Okay. Sorry about that. It is 100 bits for the curve alone, but this is the thing called ECIES, where you calculate a shared key with a key derivation function. So that was pretty unfair with the cahoots there. I gave you a bum steer, and there's no way to go back. So that's why this is extra credit, because there are various defects. Anyway, that's the point. This is what we use, what we used in the project. Anyway, all right. We'll carry on anyway. Sometimes bad things happen on the cahoots. I shouldn't stuck to just saying what was on the screen instead of going beyond it there. All right. Anyway,